Okay, so we'll go ahead and get started. For those of you who will be tuning in at a later time, we are moving on to, as you can see, gases, which we would presume are some of the gas laws that we'll be dealing with this chapter. And with that, I would recommend that you write these down. We have our first gas law we'll talk about. Okay. And really, they give these as fractions. I would prefer, although in the book they're going to show you this formula, but really what it's based off of, okay, make sure I get this right. If we had P1, we'd have V1 down there. If we had P2, then we'd have V2 up here, okay? Because they illustrate Charles's gas law in this fashion. But these are the ones, we want a nice linear equation like this, and this is Boyle's law. Okay. And then for our purposes, we'll just, we'll do the same thing for Charles's gas law. Oh, no, not that. This was supposed to be a V. Hopefully we caught that in time. Okay, so then there's a fraction here and here, and letter V. So T2 is down there, V1, V2, and then T1. Okay? And then this is again Charles's gas law. And one of the ways that we can make sense of this is one of the things to keep in mind this winter, which we've been incredibly spoiled with so far, is notice the temperatures have not dropped that far. Because one of the things that can happen is that if your vehicle is parked outside, because some families just don't have enough space to, per se, park all their vehicles inside, which would be nice, because some of you who do have to park your vehicle outside, sometimes then we got to go scrape them in the morning, or go start it and let it run for, does anyone park outside?
I do.
So, but you haven't had to, are you a scraper or are you a defroster? If you had to pick.
Depends on when I wake up, because if I
Depends on how late I am.
Yeah, it depends on how late I am.
Okay. So it doesn't bother you to scrape it?
No, it definitely bothers me. I rage every time I have to do it.
If
I
it's
actually
really
normally make
cold,
my
I
sister
really
do
don't
it.
want to, so.
I make my
Okay.
sister do it because she doesn't today. And she doesn't do anything. She just sits in the passenger seat and I drive her around. So.
You got assigned seats? Maybe you should.
In our family car we do actually, so that we don't fight.
Well, why would you do that? Why would you fight?
It's not our fault. I mean, it's not my fault. I don't fight. Actually, yeah, I do, but like,
Okay, well.
it's not normal.
So, and that's only because the, I suppose it has something with the dew point or the amount of moisture in the air. It drops below a certain temperature with, again, the humidity in the air or dew point or something to that extent. So, yes, you either scrape your windows or you got to start it up and let the defroster do that. But what might that cold weather have to deal with tires? What happens when it gets colder outside?
Makes them deflate.
That's right. And we can explain that with that of Charles's gas law. We won't necessarily need to do that today. But when it comes to Boyle's gas law, we certainly see that happen inside the valves of your vehicle. Nope. Nope. It's a type of expansion, contraction, and the combustion that takes place inside of there. Okay? So as you can see, this deals with temperature. The colder the temperature goes down, well then the volume's going to go down. Okay? So what we mean by that is a direct relationship or a direct correlation. What we mean is we've got volume and we've got temperature in this equation. So what happens is if the volume is going up, well then so is the temperature. But when it gets cold outside, like we just talked about, if the temperature is going down, what happens to our volume inside of our car tires, truck tires, whichever? Those are also going down. Okay? But when it comes to Boyle's law, it's just a little bit different. Here we have pressure and we've got volume. So in this case, if this is a direct correlation, notice that volume goes up, temperature goes up. Volume's going down, well then the temperature must have gone down. But what we see happening in Boyle's law, if the pressure is increasing, if it's an indirect relationship, not where they're both going up or both going down, here we see the volume is then going to go down. Okay? But if the pressure is going down, then the volume will be going up. Okay? And it just matters how you actually explain how that happens. And so if we have our valve, now you don't need to draw this, okay? And then here is your piston. We don't want a leak there, or else we're losing compression. Okay, so then this is attached to your camshaft, and it probably has a deal like that. So this is going up and down and up and down. So as this valve, okay, our cylinder, as this cylinder goes up, okay, so what happens to the volume inside of here? So if this is going up, this cylinder goes up towards the top of the valve, what happens to all the volume inside of there? It certainly will decrease. So we see the volume going down. Now all those molecules are running into each other and they're getting closer and closer and closer because the volume is going down. So what must the pressure be doing inside of there? That is increasing. Okay? So then if this cylinder is going down now, or this, okay, if this piston is going down now, what's happening to the volume inside of our valve? It's going to increase. Now all these molecules are getting further and further and further and further apart. The pressure is going to go down. That's right. Okay? So that's what we mean by an indirect relationship. One is going up, one is going down. In a direct relationship, when one goes up, so does the other. When one goes down, so does the other. Okay, so how do we put that to context? Well, on page 364, there's going to be some different types of, let's say, I don't want to say calculations. You could say corrections maybe, or you need to change variables from one into another. That doesn't mean anything to you right now, but we'll read about the units of pressure. Okay, top of page 364. A number of different units are used to measure pressure because atmospheric pressure is often measured by a mercury barometer. Pressure can be expressed in terms of the height of mercury in a column. Then the column unit pressure is millimeters of mercury, symbolized by mmHg. A pressure of 1 millimeter of mercury is also called 1 torr. Okay? It's named after Torricelli, who was a chemist that probably dealt with different types of pressure calculations. In the name for Torricelli for his invention of the barometer. There we have it. The average atmospheric pressure at sea level is 0 degrees Celsius and 700 millimeters of mercury. Okay. The pressures are often measured in units of atmospheres. 1 atmosphere pressure, or ATM, is defined as having exactly equivalent to 700 millimeters of mercury. In SI, or the International System, pressure is expressed in derived units called pascals. You might remember that from physical science. Okay? So that derived unit is newtons per centimeter squared, which then means, okay, we're going to derive that into just the simple PS or PC, I think we labeled it, for pressure in physical science. The unit named for Blaise Pascal, a French mathematician and philosopher who studied pressure during the 17th century. 1 Pascal is defined as the pressure exerted by a force of 1 Newton acting on an area of 1 square meter. I said centimeters, it's actually meters. Okay. In many cases, it's more convenient to express pressure in kilopascals. The standard atmosphere for 1 atmosphere is equal to 101.325 times 10 to the 5th pascals, or 101.325 kilopascals. The pressure units used in this book are summarized in Table 1, which is directly beneath this column here. One of the things that we'll be doing is measuring volumes of gases at standard temperature and pressure, and that's what the next portion of this paragraph is doing. To compare volumes of gases, one must know the temperature and pressure at which the volumes are measured. For purposes of comparison, scientists have agreed that on standard conditions of exactly 1 atmosphere pressure and 0 degrees centigrade. Okay? So if we convert that 0 degrees centigrade, we have not learned that in kelvins yet, have we? No. You add 273 to whatever your degrees centigrade is. These conditions are called standard temperature and pressure and are commonly abbreviated as STP. So our units then, as you can see, is the Pascal, the millimeters of mercury, torrs we really don't do very often, and then atmospheres. And especially with atmospheres, it's important to realize that those are some conversions that you're going to have to do. You might be given the pressure of a gas in millimeters of mercury. You may be given the pressure of a gas in kilopascals. It's important to be able to change that to atmospheres because that's the standard. The standard temperature and pressure is measured to be 1 atmosphere. And if it's the standard temperature, why can't we use degrees centigrade, do you think, with all your mathematical knowledge? Why can we not use degrees centigrade for standard temperature and pressure when we just had read that? Because what is the temperature in degrees centigrade for STP?
Minus 264.
No. You went the wrong way.
Add 264.
You would add 273, which, yeah, close enough. Because we can't use 0 because you can subtract that, but you can't multiply by 0. So that's why we would have that in degrees Kelvin instead. So what we want to look at then is I always like to add this in and read this first. Now we're going to apply it. Because when we back up to page 363, it'll make a little more sense now that we have some of these conversions that we need to do. So what that means is you can still measure pressure by using what we call these J2 columns that you see on page 363. And that might be an internal mechanism that's how pressure is measured. So we're going to make that a little bigger. We have this container here. Okay, and then what we see happening is I kind of goofed here. As this comes around, should look like that instead. Okay, So then there's a valve in here that you can see up on top. I guess I got it drawn the wrong way. I guess the valve is in here like this. There we go. And then you can open and close that. So there has to be a gas inside of here. So we could use oxygen. We're just going to use nitrogen. It doesn't matter what type of gas we have inside of here. It's just a way that as pressure from the atmosphere is pushing down on this column, if the pressure is increasing, it's going to push that mercury down in here further and further and further. But if the pressure is decreasing, well, then it's going to move further up in the column. And that's why hopefully it makes a little more sense when we deal with talking about that cylinder and a piston moving up and down inside of there. And then let's see here. I don't know if you drew this or not. If you didn't, fine. Always takes me a little bit to get this. There we go. That's what I meant to draw. Okay. So we're going to go up a little further. There. Okay. Because what happens is this mercury inside of here, notice this higher in a column on the right. And for our purposes, we call this the atmospheric arm, or AA. Okay? And then on this side, I'm going to put a dotted line. On the right side of the dotted line is our atmospheric arm. On the left-hand side of the dotted line is our gas sample arm. Okay? So I'm just going to put GA, because it makes a difference how that mercury is sitting inside of that column. So notice that you see on page 363, hopefully that looks kind of similar to what you would see inside that J tube. Okay? And this is where some of those conversions are going to be needed. That 101.325 kilopascals equals 1 atmosphere. Then also we have 760 millimeters of mercury equals 1 atmosphere. Okay, so those are our conversion units. Just like, I suppose, like you could say if you're going to Europe, or if you're going to South America, you're going to Japan, you can take U.S. currency with you, but would you be able to spend it though? Probably not, unless you do an exchange rate. And that's kind of like what we're looking at here. So I don't want to get too far ahead of ourselves, but I just want to do, for instance, one example. Otherwise, I see we're up to just about 20 minutes already. One example of making a conversion. You pick kilopascals or millimeters of mercury. Okay? So if we had 98 kilopascals, okay, we want to know how many atmospheres. Okay, so if we have 98 kilopascals, we need to have that into atmospheres. So what that means is that since we picked this one, okay, we need to get that in atmospheres, because atmospheres is your standard pressure. Okay? So therefore, it's just one conversion like this. How many kilopascals are in an atmosphere?
101.325.
So then when we do our factor and labeling, okay, where would kilopascals go in our next step to cancel out?
The bottom.
Correct. So for every 101.325 kilopascals, you get 1 atmosphere. And then all you do is divide that out. So notice that that's really, really close. So you're probably going to get something like 0.9, I'm going to go 9, 8. And again, that's just a guess. 98 divided by 101. Gives you 0.967 or 0.97. And then we label that in atmospheres. Because one of the things that you'll notice is that this is going to be measured in millimeters of mercury, okay? Because there's 760 increments on here, but you have to do a correction factor because this is open to the atmosphere. And when we measure atmospheric pressure, it's probably going to be measured in, could be kilopascals or it could be millimeters of mercury. So we need to be able to make that type of a conversion between these units. So I didn't want to go too long. We're up to 20 minutes, 21 I see. So I think that's all we have. I don't want to go much further than that until everyone returns. So hopefully not too bad. Maybe we're a little overworked. Maybe we were soaking that in with our chemistry book on top. So front row is maybe working on it or it's being absorbed. Okay, second, middle row.
I heard hair holds memories, so.
Okay, and back row. All right. So we'll pick up with this tomorrow. It says we'll be talking about Charles's gas law. I don't know if we'll get that far, but once we get everybody here, it'll fall into place pretty quickly. So we'll catch up to you next time.